Welcome to Solideo Gloria Physical Chemistry. This is the third lecture of molecular quantum chemistry. So today's topic is quantum calculation. Basically, we are doing computational chemistry kind of introduction. So firstly, we'll talk about ab initio method, and the simplest of ab initio is the Hartree-Fock procedure. And then there are several packages, chemistry software are available. One of them, or most popular, would be Gaussian Package. And then the result we can visualize with a Molden program. I picked these up for Windows. Nowadays, the Windows 10 is the current one. Windows system, PC system. Maybe if you're using Macintosh or the Linux system, you have more possibilities to choose. But anyhow, these are also available on those systems too. So yeah, so let's do some calculations in this lecture. Here is the kind of big molecule. Yeah, it's like big molecule for ab initio calculation. Remdesivir. Are you familiar with this molecule? The remdesivir, under this COVID-19 pandemic, this particular antiviral drug is nowadays recently recommended for treatment or kind of clinically tried in a number of medical institutions. So remdesivir molecular formula is here: 27 carbon atoms and 35 hydrogen, 6 nitrogen, 8 oxygen, and 1 phosphorus atoms, and there are 324 electrons. So given these atoms and the number of electrons, you are just given these fundamental particles, and then you can solve the Schrodinger equation of this system. That many nuclei, totally there are that many nuclei, 27, 35 hydrogen, etc., and 324 electrons. So these there are many. This is a many-body problem. For this many-body problem, there are Schrodinger equations like this. As the Hamiltonian and the wave function themselves are a function of nuclear coordinate, capital R, and the electron coordinate. And this equation, and we can apply Born-Oppenheimer approximation, which tells us that if there are two degrees of freedom, kind of characteristically different, then we can decouple them and solve one kind of degrees of freedom and solve the other kinds of degrees of freedom separately. Okay, and then decoupling is the key here. So basically we can decouple nuclear motion and electronic motion based on the fact that electronic motion is much faster degrees of freedom than nuclear motion. And in very fundamental or basic level, we can say that heavier nuclei are fixed in the space, and then we can treat only moving electrons in the field of fixed nuclei, just like that. So firstly, we can solve the nuclear degrees of freedom, or we can solve the Schrodinger equation for nuclear motion. So nuclear Hamiltonian and nuclear wave function, then this is the Schrodinger equation for that. And then once this is solved, we can treat the nuclear coordinate as the parameter for electronic motion. And then here, this is the total Hamiltonian and Schrodinger equation for electron and nuclear motion. And then that Hamiltonian is decomposed or decoupled for nuclear motion and the electronic motion with the nuclear coordinate as the parameter. And also then, if the Hamiltonian is the sum, then the energy is also the sum. So the total energy is the nuclear energy plus electronic energy and the nuclear coordinate as the parameter. And then the wave function itself is the product of the nuclear wave function and the electronic wave function treating the nuclear coordinate as its parameter. Okay? So that once this is solved or assumed solved, and then we can use the fixed coordinate, and then those coordinate are the parameter for the electronic problem. And the electronic problem, now we are using the colon denoting this capital R as the parameter, set of parameter in this case. And then Hamiltonian is the code as a function of the electronic coordinate, and the wave function is also electronic wave function, electronic energy, and then wave function. So at each geometry, meaning is that nuclear Hamiltonian is the wave Schrodinger equation is solved, or fixed coordinate of the nuclei, and then solve the Schrodinger equation for electron energy and electronic wave function, treating nuclear coordinate as the parameter. Once you solve this, and then depending on the problem, if you are looking for the ground state, meaning is the lowest energy state, and then you will find the lowest and lowest energy until you find the lowest energy, move your nuclei so that you're optimizing nuclear position, meaning is that molecular geometry, so that you can achieve the lowest energy. That is the procedure we call optimization. So these two, basically you compute or calculate or solve the Schrodinger equation to find the electronic energy for a given nuclear coordinate, meaning it's a conformation or the structure, and then the second thing you can do is to optimize the structure, lowering the energy. So these two are basically what computational chemistry software or ab initio method can offer you, beginning from, this is literally in Latin, from the beginning, from the given fundamental particles, you can obtain the energy and optimize the or lowest energy coordinate. This is just an example as just a simplest form of molecule. So He2 molecule, you have two nuclei and then two electrons. So total Hamiltonian is the nuclear motion and electronic motion, kinetic energies, and then electron nuclei, electron nuclei, electron nuclei, electron nuclei attraction, the photons, and then electron repulsion, and nucleus repulsion. Okay. And then with the Bohr-Oppenheimer approximation, we don't need to include kinetic energy of nucleus and only electronic energy, electronic kinetic energy, and electronic attraction to the nucleus, electron repulsion. And then this R is the parameter, and then parametrically include the nuclear repulsion energy. And in atomic terms, in atomic unit, we would say ME, electronic energy, is the unit for mass. H bar is the kind of unit, so we can treat this one, and so 4 pi epsilon 0 is also unit. Electron charge is a unit. So all these units are replaced by just one unit. Yes. So then our Hamiltonian looks like this, very simple and succinct form. So in atomic unit, our Hamiltonian is this, and then basically this is just a 2 electron problem, and then N electron and M nuclei problem is kind of general for molecule, and those can be solved in such a way that multi-atomic, multi-electron Hamiltonian is given this way. For electrons, for each electron we have a kinetic energy, and for each electron we have, and also for each electron, for each nucleus we have electron nucleus attraction energy, and for we don't count just pairwise counting, so we don't, so just electron repulsion and nuclear repulsion. And then we are solving this electronic Schrodinger equation, treating that R as the parameter. R is the nuclear coordinate. And then this wave function, total electronic wave function, if there are an electron wave function, you remember that electron is fermion, and then it must follow Fermi-Dirac statistics, meaning is that the wave function itself is anti-symmetrized upon coordinate exchange. So the best way or easiest way we can anti-symmetrize an electron wave function is to use Slater determinant. So Slater determinant 1, 2, 3 up to n electron total wave function is 1 over n factorial square root, which is a normalization constant here, and then orbitals for each molecular orbital, in this case, occupied by electron spin orbital. So electron 1, electron 2, electron 3, electron 4. So electrons in this row index and column index is for orbitals. So and also kind of simple notation for this is just to list the trace and between the vertical bar. So this is a kind of way we can express the n electron wave function. We are just reviewing this. So then we apply the variational method. Okay, and then next thing is that we'll build up the Hartree-Fock method based on this. So variational method is that this is the Hamiltonian we need to solve, and then the true energy or true wave function has the psi naught and E naught. And although we don't know, but we assume that this is known and this is our goal. And then this is the energy, and which is presented in this form. If psi naught is not normalized, and we need to have the overlap integral or normalization integral in the denominator, and the numerator itself is the just look like matrix element of the Hamiltonian. Okay, so this is the ground state energy, the lowest energy. So if we try a function to represent it that the true wave function, no matter how we do, or no matter how we try, that variational energy based on this trial function is always greater than or equal to E naught. So that's what variational method tells us, and then that guarantees us that try our best so that it can approach psi naught. Still, your energy is greater than that, the true energy. So try hard as best as you can. That's what we need to do. So that's what variational method drives us to do. So our trial wave function as a nuclear coordinate as its parameter and as a function of electronic coordinate is also an electron system and orbital product. Okay, so it's also, of course, we are counting only occupied orbitals for the ground state. So from the lowest to the top. Highest occupied molecular orbital. Yeah, so all occupied orbitals and each occupied orbital are all multiplied each other. So it's a product of orbitals, occupied orbitals, that is molecular orbital. So that molecular orbital, okay, is a linear combination of atomic orbitals, LCAO, MO. So molecular orbital is obtained by linear combination of atomic orbitals. So this trial wave function looks like this. Okay, and then a trick here is that at each time of your molecular calculation, we are not optimizing your atomic orbital, but that atomic orbital could be a linear combination of some basis functions. So each atomic orbital could be obtained by linear combination of basis function and the linear combination. This is the linear combination of the basis function that generate the atomic orbital. And then linear combination of atomic orbital generate the molecular orbital. And then your wave function is the product of molecular orbitals occupied. So that's basically this is the scheme how you obtain the variational trial function. And this is kind of implemented as a computer code. Okay, so then next step is to do, before we do that, we'll just describe what the basis functions are, or how they developed. Okay, so 1930, John Slater proposed a set of atomic orbital. Now we call that Slater type orbital because that it just looked like hydrogen orbital for hydrogen-like atoms. Remember that for hydrogen-like atom, you solve the Schrodinger equation using associated Legendre differential equation and associated Laguerre differential equation, and then for the R part, theta phi part, so angular part is just a spherical harmonic, but angular part is a Laguerre polynomial times this exponential factor. But what Slater does is get the exponential factor the same, but out of the Laguerre polynomial, he only takes r to the n-1 term for n equal n. Yeah, that's the highest degree for n, the principal quantum number n. But you have a linear combination of these to represent that hydrogen-like atoms orbital quite well. Yeah, but that's just same. This is just same. Okay, I just need a number of many terms like this. Okay, and also this is the normalization constant for the Slater type orbital. So basically, this is just look like a genuine atomic orbital. But this has this e to the minus zeta r, and that integral involving this function is slow, especially on computer clock. So people use Gaussian type orbital instead. What is different from Slater orbital is that all other parts are the same except this exponential. This is e to the negative minus zeta r. This is e to the minus alpha r square. Square and r square versus just r to the r square. And the reason for that is that if you make a product of Gaussian functions centered at xa and xb, the xa function and xb function is like that, you have a product. That product itself is also a Gaussian centered at some linear combination of xa and xb in such a way that xp is given here like this. Okay, so xp is just a numerical addition and division, and then you just make an exponent, and then another exponent is complete your product. So Gaussian multiplied by Gaussian is just Gaussian, and then integration is very quick. So we'd rather use STO for computational efficiency. But one problem here is that this is 1s orbital, and by STO, Slater type 1s orbital, but this is Gaussian type 1s orbital. Slater type has, at the nucleus, it has a cusp to the infinity, but the first derivative of Gaussian orbital at the nucleus is 0. It's a flat here. So basically they are not the same or similar. And also Gaussian type orbitals are kind of decreasing very fast compared to this Slater type orbital. Slater type orbital extend further when r grows up, when r increases. This is die quickly. So that's basically the difference. To improve this, we use many Gaussian. In this case, they use 3 Gaussians to make one kind of linear combination of these. Okay, 3 Gaussian. In this case, we call it Slater type orbital with 3 Gaussian functions. So even 1s basis function, 1s orbital, we used combine 3 Gaussian functions. So in this case, in these 1, 2, 3 are called primitive Gaussian. So linear combination of primitive Gaussian, we make a Gaussian, that is we call contracted Gaussian. So contracted Gaussian is used instead as just a 1 Gaussian function to mimic Slater type orbital. In this case, we call it STO3G. It's a kind of code name for the basis function, which is a contracted Gaussian, which is made of 3 primitive Gaussians. And this type of basis set, we use a notation something like n-mp g, that stands for Gaussian, plus or star here. So for example is 631g star basis function or basis set, maybe it's used much, so which is telling you that n, you know, there is a valence electron and core electrons. So for core electrons, we use many primitive Gaussian to contract a Gaussian functions that represent the core electrons. So in this case, 6 primitive Gaussians are used for this type of linear combination to make the core electron orbital. Okay, so that is this n. And then hyphen means that it is a split balance, meaning is that we use 2 alphas or 2 zetas. So in this case, this case is for valence electron. So valence electrons says there are 3 primitive Gaussian with one higher large exponent and one low exponent. So if exponent is greater, then if greater the exponent, then it's much more close to, meaning it's a very narrow to the nucleus. If that exponent is smaller, then it's much diffuse. That's why the valence electrons are represented by 2 sets of Gaussians. So that's NP. In this case, there are, for the valence electron, 3 with larger exponent and 1 with a small exponent. Primitive Gaussians are used to make the linear combination to represent that valence electron. And then G stands for the Gaussian, meaning is that these functions are Gaussian, and then there would be star or plus sign or both. So 1 star means other than core and valence electrons, 1 more polar. In this case, it depends on the case. Like d orbital or p orbitals are used. That star means. Or if you have double star, stars for 1 star for the non-hydrogen atoms. Okay, but 2 stars both hydrogen atoms and also non-hydrogen atoms. Okay, so that's what the star or double star mean. If you have plus sign here, then you use diffuse functions so that you can represent kind of diffuse electronic system like anions as such. So that's what the notation for notation format for the basis functions. There are many, something like 321G or 321G star or 6-311G plus star, just like that. Okay, so now we are ready to do some kind of explain about Hartree-Fock self-consistent field calculation. As I said, Hartree-Fock is the kind of very basic in ab initio calculation. So historically, in 1928, Hartree proposed a product wave function for multi-electronic system. So his suggestion is just to use orbital product to represent he called it, or we call it, Hartree product, the molecular wave function. And then his this electronic or the electronic Hamiltonian, treating the nuclear coordinate as the parameter, is just electronic. Just the same as before, electronic kinetic energy and electron nucleus attraction, electron repulsion, nuclear repulsion. And then in order to solve this, what we do here is that we assume a set of orbitals, these orbitals are available, known. And then we pick up one electron, and then that electron, let's say just number 1 electron, that number 1 electron moves around in the field of 2, 3, 4 to n electrons. So move in the field of other electrons. So that's what we call J. It's effective electronic field for electron I of J. So which is a kind of Coulomb integral just like this. So Uj is in the field of J. It's a Uj star and Uj, and then the expectation for 1 over Rij. So this is the field of electron J for electron I, or that's the field electron I experience due to electron J. So this is the Coulomb field of electron J. Then effective Hamiltonian is the for I, effective Hamiltonian for electron I is the electron I's kinetic energy and electron I's nuclear attraction energy, and also then the sum, not J not equal I, electron energy, this energy, Coulomb energy, and also this is just a parameter for nuclear arrangement. Okay, but you notice that the electronic degrees of freedom is only electron I, or electron I's coordinate, or electron I's coordinate is the only independent variable for this, so that this Hi effective is effective Hamiltonian for electron I. Then you can solve this is one electron problem, and then you find what? One electron problem, you find that electron I's orbital, yeah, okay? So you just solve one electron problem. So basically, Hartree procedure is to reduce an electron problem into one electron problem, but you assume other electrons. So what do? You pick up one electron, and then two n electrons are fixed. You find one electron, and then next time you pick up electron number 2, and then you electron number 1 and electron number 3 to n are kind of fixed, and you kind of calculate electron number 2, just like that. So complete that cycle so that you determine electron 1 to electron n, and then compare this to the previous assumed electron orbital. If they are the same, you're done, but if not, you repeat that procedure. That is described in this flow chart here. So firstly, you guess or kind of guess, initial guess we call, assume certain molecular orbitals for each electron, and then you obtain this Coulomb integral for I electron I due to electron J, and then with this Jj, all J's except electron I, you assemble this effective Hamiltonian and solve this effective Hamiltonian Schrodinger equation, obtain the orbital energy and the orbital. And then you do that for electron 1 through electron n and compare to the previous ui-1 to ui current 1. If those are the same, and then you've done it, you achieve the self-consistent field. Okay. Otherwise, you repeat this until you fulfill this self-consistent condition. So you have done, and then you collect all the electronic orbital energy, and then product of those orbital, you will obtain the wave function. This is the procedure. But the problem is that you forgot what? Antisymmetrization. So later on, a couple of years later, Fock antisymmetrized the Hartree product wave function, and then obtain Fock operator, and then use this Fock operator instead of effective Hamiltonian, and then you do the same iterative method that is self-consistent field calculation. And then we call, then we make a kind of matrix format, kind of a computer algorithm to do it. So we call it Hartree-Fock method, and then based on this Hartree-Fock method, it determines orbital energies, and then summation of sum of the orbital energy up to the occupied orbital. That will give you the energy. And also you remember that your wave function orbital is a linear combination of atomic orbital, which is also a linear combination of basis function. So Ci is the linear combination coefficient are determined in this kind of iterative process, then that's the wave function. So this is the kind of algorithm, and once this is self-consistent field linear combination of atomic orbital, molecular orbital wave functions, And then whatever the best you achieve, okay, meaning is that use the bigger basis set, meaning more and more terms, and then more flexible wave functions, then you will certainly lower the energy. Then no matter how you do, or you utilize all kind of possible ways to make it flexible trial function, and then increase the number of basis functions as such, but you may not be able to lower the energy. Then you reached the Hartree-Fock limit. Okay, so you reached the Hartree-Fock limit, and then that's the best result you can obtain by this variational principle, or by this Hartree-Fock procedure. And then of course you had known, or the goal, which is that exact energy, and the difference between the exact energy and the Hartree-Fock limit is the correlation energy. So correlation energy is the difference between the exact energy and the Hartree-Fock energy for the given basis set. Okay, so people devised the method to improve or lower the energy, and those are available in the computational chemistry package. So firstly, the basic, or the kind of fundamental, is the Hartree-Fock method, and then this is the variational principle, and then MP2 or MP3, MP4, those are Miller-Plesset perturbation method. So perturbation improve Hartree-Fock result, and also there is a CI, configuration interaction, meaning firstly, Hartree-Fock, how many basis function, how many wave function? The wave function was slated determinant, so one determinantal wave function, which is usually ground state. So all occupied orbitals are included in the slated determinant, or the product that makes the total wave function. That is one configuration. More configurations could be possible, such as excited state. Then you add that as a slated determinant. So this is more than two slated determinant for one slated determinant for each configuration. So many configuration, and then let them interact. So the name for it is the configuration interaction. Okay? And also density functional theory method, which is not really for the correlation, but sometimes you achieve better low energy than Hartree-Fock method. So it's one variant of this computational approach. These are available as a key name or keyword for computational chemistry package. We'll just do the Hartree-Fock today. Okay, so in order to use computational chemistry software, you need to tell the molecular shape or molecular structure. Molecular structure, in terms of general chemistry, we say that what is molecular structure? Which is that the geometric arrangement of atomic nuclei. Okay, so that's what molecular structure is. So where the atoms are located. We use G matrix to tell the molecular structure. So G matrix looks like this. Actually, this 0 and 1, 0 is the charge and 1 is the multiplicity, and this you will see in Gaussian input file. So I just placed them here, but they are not a part of the G matrix. G matrix begins just here. The first atom, second atom, third atom, and fourth atom, just like that. The example here is for hydrogen peroxide, H2O2. So I place O1, I name just the atom oxygen 1, oxygen 2. O1 at the origin. Okay, so O1 at the origin, 0, 0, 0. O2 in the convention is on the z-axis. Okay, so O2, 0, 0, 1.474 angstrom. So this is the g-axis. I'm sorry, this is the g-axis. Okay, g-axis. Okay, just like that. And then the distance is 147.4 picometer. This is 1.474 is angstrom. default unit for Gaussian package is angstrom and degree. Okay, and so the G matrix tells us that O1 is at the origin, O2 is connected to O1 by the distance R0, ROO. ROO is a variable here. I could have placed 1.474 here instead, but I am using a variable ROO 1.474, just like this. And here you note that there is a blank line here. Okay, O2 bonded to O1 and this much distance, and He2, which is bonded to O2 and angle to O1 with angle ROH. I'm sorry, this is I made a mistake. He2 is bonded to O2. He2, this H2 bonded to O2, and the distance is ROH. So ROH is this, actually the same as this one, and this, and then that connected to O1, making angle, this angle. This angle is AHOO. Okay, so basically third atom connected to the previous atom and then angle to another previous atom. That's the way it is. But actually this is just connected to this, to oxygen 2 and oxygen 1. So H2, O2, O1 order, H2, O2, O1 order, and this is a bonding, and this H2, O2, O1 is an angle, AH00. Okay, and then this I call H1 because this is H2 connected to O2, this connected to O1, so I call it H1. H1 connected to O1, and then angle to O2, and then make a dihedral angle to H2. So basically what does it tells you is that H1 to O1 distance is ROH, in this case 95 picometer, and make an angle to O1 as 94.8 degree, and making dihedral. Why we call it dihedral is that is a plane, that is the angle between the plane making HOO plane and OOH2 plane. So that is the angle between these two planes. Or how you obtain is that you look at from this direction, get this direction, then through this O axis, then the angle between this OH bond and this OH bond. That's the angle making. I'm actually looking at from this direction and make a clockwise look. So look from here and then this, and then rotate to 111.5 degree, you will meet this OH bond. So that's the DHA-OOH dihedral angle. So this is the bond distance or bond length and bond angle, dihedral angle. So first column is the atoms, and then second column is the where it bonded, and then bond length, and third 1, 2, 3, 4, fourth column is the where it makes angle and angle, and then 1, 2, 3, 4, 5, 6 column is that where it is for the dihedral, which and then dihedral angle. This is what we call G matrix. Okay, and then one blank line, and you list all the variables and then initial values for those variables. When you make a geometry optimization based on G matrix, and then you need to say, or you need to specify which variables you optimize, or these variables are moved or kind of changed along the optimization steps. Okay, so this is our kind of presentation for basics for quantum chemistry calculation, and then I would go further with some demonstration using Gaussian package on here the notebook Windows 10 system, and then use Molden Molden software for Windows. So that's what we do. So let me prepare for that. Okay, bring up some example just here. So this is one input file for Gaussian package. So you can use any Gaussian program. I think today is 2020, so maybe there is a G20 packages available, but there are, as far as I recall, in my computer system, I had Gaussian G09, or previously I had G03. I know there must be more recent version, and I used the G98, probably G92, and even G80, Gaussian 80, something like that, years ago, a long time ago. I remember Gaussian 86 was there in when I was a student, long time ago. But anyhow, so this is one example for a Gaussian program, and this is quite kind of universal for Gaussian systems. So Gaussian, there is a percent command there, but there is this pound command, which are called root card in ancient versions, but root sections. Okay, root sections tells Gaussian program what to do for you. So in a way, this and also that is kind of denoted. The root command is denoted by this pound sign, and then P is just a print. So if you don't say P, it will just tell you essential things to let you know it has been done. But if you say P, it is kind of verbose printing, I think. Yeah, verbose printing. Yeah. So it just print what it does. It kind of gives you more printing. That's what it does. And also HF means that it's a Hartree-Fock method. Here, if you say DFT, meaning it's the DFT method, or MP2 doing MP2 calculations, just like that. So here we are doing HF, and also we are doing H2O, not H2O2, because H2O is simple, and also you have done this on your symmetry work and also your vibrational analysis like that. And then so we'll check our normal mode after we have done the calculation. So we're doing H2O, and then we are going to use 6W1G star basis function. So what this is a method and basis function. So method slash basis function. That's what this command tells Gaussian system to do. And also here are these two. GF input will print out the basis function. Okay, and IOP is the kind of link specification for the Gaussian, how to perform the calculation, I think. And 6/7 = 4. These two were required by Molden program for old versions of Gaussian. So I'm using this lecture, I'm using Gaussian 09. That particular version does not require this, but for some older version, probably you need this. That's what Molden documentation said. And also what I'm going to do is optimization, meaning is that I'm going to minimize the structure, optimize the structure for the lowest energy. Then that will give us a optimized structure. The initial is the 0.96 ROH OH distance, and HOH angle is just a tetrahedral angle here. So this is the initial condition or initial geometry, and from the initial geometry it will optimize achieving lower energy. And also I'm asking it do frequency calculation. So it will generate the second derivative and then diagonalize it, and then will give us that frequency. And then there is a blank line, and then there is the kind of title or the kind of your comment describing what the calculation involves. And also another blank line. And then, as I said, 0 is for the charge and 1 is the multiplicity. So this is the singular calculation. And then first atom oxygen and second atom and third atoms are all hydrogen. And here, instead of using the atomic name, we used O1, H1, O2, H2 for the hydrogen peroxide. In the case, there is no such thing. It's just oxygen, hydrogen, hydrogen. So 1, here is the first atom. And 2 is the second atom, just like that. Instead of atomic symbols, we just used its place, the first place and second place. So this H is connected to first atom, and then the distance is ROH. And this H also connected to first atom, the distance is ROH. And then angle to the second atom, which is H. So the angle is HOH. Okay, and the angle is the AHOH. And ROH and AHOH after the blank line are variables and declare their initial values here. Okay, and then that's the end of the Gaussian input file. Okay, so you've looked at the Gaussian input file. Okay, and then we are going to open the Gaussian 09 window version, and then we'll open that the Gaussian input file. I named it, I think that HOH or H2.gjf Gaussian jar file. Yeah, Gaussian GJF. Right? H2.gjf is the file on the desktop. Just this one. And then there is a percent section that tells the hardware to do such a thing, like memory use. Memory is up to something like 8 megabaud, something like that, and then designate the checkpoint file. So that is going for this percent section. And then root section is just as I told you, that the pound something root section. When it reads this Gaussian jar file, it just places those things to Untitled section, and then charge and multiplicity, and G matrix, the molecular specification section, just like here. And then what you can do is that click file and then exit and run. Exit and run, and then it will run, but it asks us that which output file. So I'm going to get no, not that one. I'm going to get in the this one. Actually, I've checked this before. So I run it onto the desktop. So I will just do just like that. But if there is a file like this, it asks if it overwrites it. I say okay, just overwrite, and it runs. It runs, and then that run is showing here, and also that echoed into this file, h2.out file. And then it has the normal termination of Gaussian 09 at May 29 today's, and then this is the hour. Yeah, it's pretty okay. Yeah, it's not that late. And then there is something, and then kind of archive punch, and then just like that. So we are going to look at this in more kind of readable form. So I'm going to quit, and then we'll bring this out. Okay, so this is the result. This is the result. And then it says that some copyright thing, and then some things that you use Gaussian program against them, meaning it's the producer, that's okay, but some citation. And then this is Gaussian 09, and then today's date, and this is the first line of our input file. So root section, and that root section organized this in this form. They're running. Then our title and our symbolic G matrix we input, and charge and multiplicity see here, and then our initial variables. Okay, so this is basically what we see. Our input file is correctly accepted by the Gaussian program. Okay, and then it analyzes our input and then do kind of reasonable thing. But let me just give you a note here. First line, add a, just like this is a kind of magical one line, which is the entering Gaussian system. Just one line there. The reason for this line is very funny. Actually, it has nothing to do with your Gaussian run, but the Molden program, I'll explain later, requires this line. If you don't have this line here, it will just don't process the output file. For some reason, if you run this Gaussian program from your the server, Linux system, or Ubuntu, whatever, Linux version, and then it put just that entering Gaussian system there. So because I ran this on window, it doesn't put there that particular signal there. So you must have this. So I just manually typing by system echo here by myself. So you have this line, and then you are safe to use Molden present this output file, but you have to save it. Okay, so that's done for Molden, and then we have looked at up to here. So this is the initial parameter. You begin your first single point calculation from here, and then you remember that your first atom is in the origin, and then second atom in the z-axis, and third atom in the xg plane. Okay, so x and z, no y's, all y's 0. Okay, then and also it is C to V symmetry, and because I intend to have it the same ROH distance, so it is symmetrical. And if you don't want to impose the symmetry, meaning is that you want to complete minimization, then you use different variable, and also in the root card or root command, say no sim command, no sim, NOSYM, then that calculation won't use this symmetry. Okay, then it the GF input we just put list this basis function, and we are using 631 G star. So oxygen is the second period, so the core electrons we use 6 primitive Gaussian to represent the one contracted Gaussian, and then the valence electrons. So second period, valence electrons we use 2 sets with large zetas and one small zetas. So these 2 sets of primitive Gaussians are used to represent that contracted Gaussian function, and also 631 G. This is the G. I'm sorry, a Gaussian, but 631 G star. This is star. You use polarized Gaussian, which is D function. Okay, so this is what it is for oxygen atom, and for hydrogen is only the first. Is also already a valence electron, so there is no more. So it use only 3 contracted 3 is primitive Gaussian as a because 3 itself is what the 1 electron, but those are that is also valence electron. So 3 1, yeah, 6 not 3, but there is no core for hydrogen, so 3 1 combination is for the electron. So it uses these two sets of the large exponent and small exponent Gaussians. So this is also hydrogen. So, and based on this, there are 19 functions. Then it says that 10 A1 functions and 1 A2 functions, 3 B1 functions. You know, these are from the symmetry, totally symmetric and anti-symmetric against the rotation, seat rotation, and symmetry against the plane and anti-symmetry against the plane, just like that. Okay, and then 5b2 symmetry orbitals, and then you combine only these orbitals to make A1 orbital, combine these orbitals to make B2 orbitals, as just like that. Symmetry adapted linear combination, SALC, symmetry adapted linear combination. SALC generate molecular orbitals. Okay, and then you do that, and then basically occupied orbitals are these. Actually, we have seen this by analyzing the SALC orbitals based on the symmetry. Okay, that's what. So this is 1A1, 2A1, and this is 1B2. Now this 3A1 and 1B1 orbital in our notation. So then, now we are ready to begin the SCF cycles. So this is SCF cycle. This is the closed shell calculation, or RHF calculation, restricted to the Hartree-Fock, meaning is that there are same number of alpha electron and same number of beta electron. This is, in this case, there are 5 alpha electron, 5 beta electron, just like that. And also the algorithm we are using is the DIS extrapolation algorithm. And yeah, this kind of SCF iteration algorithm. And then it says cycle 1, the energy, and then cycle 2, okay, and cycle 3, cycle 4, cycle 5, cycle 6, cycle 7, cycle 8, cycle 9, cycle 10, and then it converges. So SCF is done, and then the energy is calculated, and then convergence criteria is like that. Okay, so given the geometry, initial geometry, you achieve the self-consistency at the 10th cycle, and then you have the energy for that conformation. Okay. And then you analyze your orbital. So your A1, B1, B2, B1 orbital, the orbital eigenvalues are orbital energies and occupancy is there. So first orbital A1, which is, you remember that is oxygen 1 S orbital, that is co-electron. Co-electron. So it's just kind of non-bonding. So it's O1S contributing 99.463% of it. But actually, that's not that percent. That's just coefficient. So coefficient square is the contribution, and also other contributions there because it's a linear combination of all basis functions there. And yeah, so but mainly it is oxygen 1s orbital, doubly occupied, of course. And then this is also some inner 2s orbital, maybe 3s orbital, just like that. So anyhow, so these are up to 5 orbital 5 are occupied, and all are virtual. The rest of them are virtual. And then orbital contribution, I mean basis function contributions to that orbital. Here the 4 means that this is that d orbitals with 6 different d orbital representation. We make a linear combination of these to make a 5 d orbital representation. That is it. Also, it has some molecular atomic charge calculation, and then dipole moment into g direction is like dBi, and then quadrupole moment, then octupole moment, and hexadecupole moment. This is molecular property. Okay, and what else? Orbital energy is done just like that. Okay, and what it does at this point, it calculates, I think that forces on each atom, and you know, and then if geometry is optimized, fully optimized, there is no force. So force is the first derivative, okay, in energy. So it calculates the force, and then criteria does not meet, so it calculates the next point in geometry. So the next nu x is calculated here, and then the atoms are moved the next geometry. Okay, and then in the next geometry, it begins the calculation. Again, the SCF cycle again. So SCF cycle, so 1, and then cycle 9, and then SCF done, and in the low energy. Okay, if it goes higher energy, then it goes back to the other direction. Okay, then it says then, and then it computes another force about those atoms, and then it says that not converged. It basically there are two criteria: maximum force and RMS force. Both has some threshold values, and those are larger than the threshold values. And also the displacement. The first step there is no displacement, but from the second step, once first step's done, and then looked at the second step, it can compute the displacement required to achieve next step, and then that value compared to the threshold, and that is greater. So nothing converged, so then to move the position and then do another calculation until lower and lower the energy, and then check the convergence criteria, and to meet the convergence criteria, and then it stops. So it does one more time, third time, and then let's say all converged. So it converged at the third step in this case, because I already gave kind of good initial geometry. And then what you see here, optimized parameters. Initial parameters, then optimized parameters. For some reason, your calculation does not converge. Why? Because the default value of this number of iteration of optimization step is 20. So obviously we have done only 3 steps, so it's before the 20, so it's optimized. If not, it says non-optimized parameters, something like that. And if your geometry is very complicated, and then you expect more geometrical step is required, then what you do? You say just optimization equals max step equals what? Maybe 60 or 100, something like that. Then it does run 100 step. What if it still does not converge, even if it's spent that much time for 100 step? What you do? Then either you copy this non-optimized parameters, start over, or you utilize the checkpoint file. From the checkpoint file, you can restart. Okay, so that's kind of thing you can learn from the Gaussian. If you're using Gaussian, of course. If you're using games, then games. If you're using Turbomer, if you're using, I don't know if still they use Jaguar, but if you're using Jaguar manual, those will teach you what those parameters are, and also how you utilize them. Okay, so you obtain this. You remember that this was 0.96, so it's kind of decreased by about 0.13 angstrom, and then this was 104.47, so 1 degree difference optimized. Okay, so then you will get low energy for those. Okay, so you have done basically achieved what? And then this is a final analysis of your orbitals, and basically you completed your mission for geometry optimization. So that's first step. So this is actually, I asked 2 things, optimization and geometry, the frequency calculation. So these 2 things, the Molden people ask us not to do, separate them, but I just did that for this version. It accepted it, so you may do that too. So it says that there is a normal termination for the Gaussian job. First, here I now begin this frequency calculation. So frequency calculation is done. So with the initial that's why I use this optimization. I mean, combined job, compound job. So used this optimized parameters, and this is a kind of extra thing I need to tell you is that when you do frequency calculation, you must use the optimized geometry, the lowest energy. There, you just do the frequency calculation. So if your geometry is not optimized, then your frequency calculation is not so meaningless, I would say. Yes. And then do the same thing for the calculation, and then actually does the calculation once, and then with that it does frequency calculation. Once it does frequency calculation done, it lists all the frequencies. Now, how many frequencies would you expect here? 3 atoms, then 3 times 3, 9 degrees of freedom. So you see 9 frequencies. So there are 3 frequencies for what? It's just not meaningful, but those for translational degrees of freedom. And other 3, these are for rotational degrees of freedom. And then these rest of these, which is big numbers, high numbers like these, then these, yeah. These are genuine vibrational frequencies. Okay, yes, there are. So there are these according to their symmetry, which is based on these translational vectors. Translational vectors. Atom 1, atom 2, atom 3. I'm sorry. Atom 1, atom oxygen, atom 2, hydrogen, atom 3, hydrogen. Coordinate, XYZ coordinate, okay, based on this. This is A1 totally symmetric vibration. This is also another A1 symmetric vibration. This is B2, in this case, kind of B2 symmetric vibration, yeah. So 3 frequencies are here. And also, you have rotation calculated and vibrational calculated, electronic calculated. Then what you can do is thermochemistry. You just obtain your partition function. From the partition function, you can obtain energy and free energy and entropy even, yes. So those things are done here. Energy, CV contribution and entropy contribution and all others. And also this will generate not so meaningful, but IR spectrum and Raman spectrum. Because you have 3 frequencies. And also your symmetry analysis will tell you that this is water molecule is IR active and also Raman active, and also this is this shows you that's true, and also some intensity comparisons is reported here. Okay, so basically this is it. This is what you learn or obtain information from Gaussian output file. And usually the kind of I would say beginners anxious to look at just this normal termination only, and then pretty much happy about it. But I do recommend my student to read thoroughly as possible, the output file, and learn from that about his or her molecule, okay, and understand all aspects of the calculation done. So it says stationary point and what the stationary points are as such, and then that will tell you what is involved in the molecule and in the calculation, and the kind of the meaning, scientific meaning, or about his finding of this calculation. Okay, so once you have done this, I think I have to save it, because I put entering Gaussian system. Okay, we can now use Molden. So Molden, you obtain Molden from the distributor. Actually, just a kind of search for Google or any other search engine, say Molden, MOLDEN. Probably the keyword is Windows 10, and that will direct you Windows 10 version of Molden, and then obtain that and unzip, and that will produce this Molden directory. In the Molden directory, there is a Gmolden. This is the kind of program you utilize it. And then what happened here is that what it was is the previous version is kind of old version. They used to develop this Molden program for Unix-based system. So X window was a kind of default window engine. So it is only available for X server. But Windows, you have to run X server passively so that you can run Molden. But from certain version, just like this, actually I found this only this year. I didn't know last year. So the Windows version Molden is available. This one does not require you install X server. There is an X server for Windows version X server available, but sometimes you have to pay it. Not sure there is a free version available, but anyhow. So this one is good, although you have to kind of tweak a little bit about the Gaussian output file. Or I'm not sure about other games or other output file, but at least for Gaussian 09 version, you have to put that entering Gaussian system, just one line at the top of it, of the output file, then you can utilize it. Okay, so this is some Molden control. It's just a very look like X Windows system. So Molden control, and then this the skull and bone is the exit button, but we are not exiting. We are instead of reading the Gaussian output file. So if I push the button, it just open another window, and then it lists the directory. This is the Molden directory. You recall that the Molden directory, I don't need this one. Molden directory is here at the desktop. So, and also your output file is also desktop. So we'll just go up. This double dot is mother directory. Just go up, and then voila, there are GJF file and out file here. So this out file, if I click it, voila, it is here. If you don't put that entering Gaussian system, it never show up. So that's the kind of magic word for that. So this is the output we have read. Okay, and then we don't need this anymore. So we have read it. I don't need this anymore. Yeah, we have read it. I want yeah, instead of rotating it, I just wanted to move this one, but it doesn't move. Okay, that's fine. Then I will use from, maybe it's better this way. There are many things we can do. If I click this one, it's the first one. Next, it kind of shows the kind of each steps in the optimization. And then another step, it doesn't move much. So I can check how it is converged geometrically. Somehow this SCCF convergence does not really tell you much. So, well, actually this is the fourth. So first step, this is the energy. First step energy, second step energy, third step, and then it is also optimized at the third step. So that's the final, these 2 points are the same. That's for the checking. And then force. So force is reduced, and then steps also. So basically what it shows you is each step. Okay, that's first step, and then second step. See, you just move that. For example, first step, second step, and third step. It does not really move much. Third step, yeah, see, very small movement at the end. So this is the same. So this shows you how the optimization is done. Okay, and then also you can check the distance. What it does is the first atom and second atom, and then it's the distance is 0.947 angstrom, just like that. Okay, maybe you can check the angle, and also check the there is no diagram. Actually, this molecular geometry you would check, and also, oops, where is that? Yeah, this one. And also, what you can do is that instead of this kind of line drawing, we can use the ball and stick. Yeah, ball and stick. And then instead of shadow, we have a little lighter ones. Okay. And I want to kind of decrease a little bit. Yeah, yeah, it's much kind of look nice. And then I'm going to show you the normal mode analysis now. Yeah, it says that there are 1, 2, 3 vibrations. So this is the you remember that kind of low frequency A1 vibration, yeah, something like that. It was a bendings or totally symmetric bending, yeah, and also some stretch mode at the higher frequency. So let me just show you, yeah, this vibration. This is that vibration, okay. Just look. Yeah, what does it look? It is just looking like symmetric bending motion, symmetric bending. I see, you don't see it. Yeah, okay. Let me just move it down so that this is symmetric. Yeah, symmetric bending at frequency is 1827 wave number. Okay, it's very strong intensity. Okay, and that is also A1 symmetric bending. Okay, and also this one is weak, which is symmetric. Okay, that is symmetric. Yeah, symmetric stretching. And this one is a little bit stronger, which is anti-symmetric stretching. So basically, these are we have already looked at from our symmetry analysis using character table. And also this could be done by Hessian diagonalization. And also when you do Gaussian calculation and do frequency calculation, then you can, and using Molden program, utilize the molecular vibration, normal mode, visualize your normal mode. And also using Molden, there is a way to present your molecular orbital, and that will help you analyze your reaction mechanism as such, many other things. Okay, this is a kind of, this is a end of my quantum chemistry calculation lecture, and thanks for, I don't know, this is about 80 minutes now, so thank you for your patience, and let's learn this one by one and the legend tree. Okay, thank you.